Hello there, Year 9s, Mr. Herman here, and this is exercise 5H, solving quadratic equations by completing the square. The learning goals for this lesson is to understand that completing the square can be used to help factorize a quadratic equation when integers cannot be found. And the success criteria for this lesson is to be able to solve an equation by using the completing the square method to factorize, and to recognize a form of quadratic equation that gives no solutions. So in exercise 5e, we looked at the methods of completing the square. We weren't exactly solving for quadratic equations at that time. We were just honing in on the skill of completing the square. And what we're going to do for 5h is utilize that skill, and then with the completing the square method applied to a quadratic equation, we're going to solve for that quadratic equation when it's equal to 0 using the null factor law. So to solve quadratic equations in the format of ax squared plus bx plus c equals 0, if you cannot factorize this, you're going to complete the square for the quadratic expression, factorize if possible, and then solve the quadratic equation using the null factor law or any other type of method. Before I get to the second dot point here, this format, when you can factorize, you just factorize it like normal using null factor law, and then you can solve for x. But there are going to be scenarios where you cannot simply factorize. So this is where, a bit of a recap, you take what the coefficient of x is, in this case it's b, you half b, and then you square it. So if you remember what we did in exercise 5e, you obtain what b is, you half b, and then you square it. And then that will help determine what you can add onto this part here, and then also subtract it to balance it out. And we'll look at the examples here to show you how that's done. Just be mindful that expressions such as x squared plus 5, or something like x minus 1 all squared plus 7, these cannot be factorized because there's no way that we can fully factorize this any further. This can't be factorized because it's positive, so you can't use the difference of perfect squares. And this right here, it can't be factorized anymore. There's nothing else that can be done to this. So no solutions can be found in this case. It goes from this premise here. If we take the most basic premise of x squared plus 1 is equal to 0. If you were to solve for this, if we were to subtract 1 from both sides, we will get x squared is equal to negative 1, and then we square root both sides to get x by itself. X is going to be equal to the square root of negative 1. There are no two numbers that when you square root it will give you negative 1. It can't be positive 1 because 1 times 1 gives you 1. And it can't be negative 1 because negative 1 times negative 1 gives me 1 as well. So this here proposes these many difficulties. It's unsolvable, at least for the real numbers. When you get into complex numbers or imaginary numbers, if you decide to take specialist mathematics for units 1 and 2, or even 3 and 4, you will delve into a proposed solution for this. But generally speaking, these don't have any solutions whatsoever. So let's have a look at these examples. There are 3 examples for this. We're going to tackle all 3 so you can see how we can solve by first completing the square. So A here is x squared plus 4x plus 2 is equal to 0. Now this format here, we cannot just simply factorize because there's no two numbers that when multiplied will give you 2, but then when added will give you 4. So we're going to complete this square. So we're going to take this b, so this b value is 4, the coefficient of x is 4, so b, I'll make that a different color, so b here is equal to 4. If I half 4, so from 4, if I half 4, I will get 2. And if I square 2, this will give me 4. So it's kind of weird, we're going 4, back to 4. This number here is not 4, it's a 2, so this is why we can't necessarily factorize this normally. So we will have x squared plus 4x, and we're just going to add this 4 and then take away the 4 to balance it out, with this plus 2 tagging along, and this is equal to 0. So now, breaking this up into 2 different parts, we can factorize this, and then we can deal with this at the end that's tagging along. So x squared plus 4x plus 4, this then simplifies to just x plus whatever this term ended up being. So this is x plus 2 all squared. And then we have this negative 4 plus 2, which is just minus 2, which is equal to 0. Alright, so there is completing the square part. Now what we're going to do is force this to be difference of squares. So because there is a difference involved, this can be written as x plus 2 plus square root of 2. Remember, this isn't a perfect squared number, so you just force it to be a surd. And then x plus 2 minus the square root of 2. And this is equal to 0. So now we've got these 2 terms here being multiplied with each other. That's going to be equal to 0. This is where the null factor law gets into play. So this is implying that either x plus 2 plus the square root of 2 is equal to 0, or x plus 2 minus the square root of 2 is equal to 0. So what do these have to equal to 0? Both of them in these cases. So to solve for x, we can just minus both of these terms here. So this implies from the first one over here, if I subtract 2 and subtract square root of 2, x will be equal to negative 2, take away the square root of 2. There is our first solution over here. Or the second one here, if I'll subtract 2 from this one and then add square root of 2, x is going to be equal to negative 2 plus the square root of 2. And here is our second solution. The formatting of how this is written might be a bit different. You may see that it might look like this. You might get a solution that says x is equal to negative 2 plus minus the square root of 2. They've just implied that the plus and minus is put together. That being what might show as one plausible solution within your within the answers at the back of the book. All the positionings of these numbers might be switched around. It doesn't matter as long as you show that the working out prior to answering this question is all correct, and the answer follows one format or another that is correct, then that's completely fine. Question B is x squared plus 6x minus 11. So x squared plus 6x minus 11 is equal to 0. We're going to look at this b. This b value is equal to 6. So from 6, we're going to half this. This gives me 3. And then we're going to square it, which gives me 9. So I'm going to put this x squared plus 6x. I'm going to add a 9. I'm going to add 9. But then I'm also going to subtract a 9 to balance it out. I have my minus 11, and this is equal to 0. So now we'll break this up into 2 different parts. There's the first one. So this here gets written as x plus 3 all squared. It's always whatever this middle number is that goes within here. Minus 9 minus 11 gives me minus 20. And this is equal to 0. Alright, we can have a difference here. We're going to force this to be a square, so we'll just write it in the form of a surd. So this is going to be written as x plus 3 plus square root of 20 multiplied by x plus 3, take away the square root of 20. And this is equal to 0. So this implies that either x plus 3 plus root 20 is equal to 0, or x plus 3 minus root 20 is equal to 0. Now I've been a bit lazy here. I've skipped not necessarily skipped a step. I prefer to put the step prior to writing this out, but this here, both of these can be written as x plus 3. Remember, this surd can be simplified. There is a factor of a square number within here, which is 4, and this can be written as 4 times 5. The square root of 4 is 2, so this is written as 2 root 5. This is going to be equal to 0. By now you should be able to write this step from here to here with small numbers anyways, without having to show all the different working out. The square root of 20 is equal to the square root of 4 times the square root of 5, etc. You can just go straight from here to here. And conversely, this one here, x plus 3 minus 2 square root of 5 is equal to 0. And now what we do is just simply solve for x. So this implies here that x is equal to negative 3 minus 2 root 5, or x is equal to negative 3 plus 2 root 5. Remember, all I'm doing is applying the inverse operation to get x by itself. So I'm subtracting 3 on both sides and then adding 2 root 5 to both sides. Here, subtracting 3 and then subtracting 2 root 5. Again, this can also be written as x is equal to minus 3 plus minus 2 root 5. All of these solutions will suffice. Alright, question C over here. This is x squared minus 3x minus 11 is equal to 0. I'm just going to write it here again. X squared minus 3x minus 11 is equal to 0. Now, we're going to stumble onto fraction territory because of the fact that b is a odd number. So what will happen is, because b is equal to negative 3, from negative 3, half of negative 3 is negative 3 on 2. Now, I don't want you guys to write negative 1.5 because when you square that, it gets into tricky territory. So keep it as a fraction. And then when you square this, this will be 9 on 4. I had to pause that. My wife just came in and pointed to me and said, "You're a square." When I say square the number, her payback will be coming soon. Anyways, negative 3, half in it, and then squaring it. The negative disappears because when you square negative number, it turns into a positive. So I'm squaring the 3 on the top and squaring the 2 on the bottom. So we are adding 9 on 4. So this here will be x squared minus 3x plus 9 on 4, take away 9 on 4 minus 11 to equal 0. Now, just realize that the example within the textbook, they've actually made a typo with this here. They've shown this to be a minus 11, but this actually should be a minus 1. That should be a minus 1 there. So that doesn't necessarily change too much. Just kind of do that. I could have attempted to make this minus 11, but I don't want to get the numbers too tricky to show for the example's sake anyways, so we'll just keep it consistent with negative 1 or minus 1. Now we'll group that there with that. So this ends up factorizing to x squared and whatever this term is, so minus 3 on 2, not x squared, x all squared. Sorry, I'm still thrown off by the fact that my wife called me a square. And here, this is minus 9 on 4 take away 1, which is the same as minus 9 on 4 take away 4 on 4, because 4 on 4 is the same as 1. Minus 9 take away another 4. Dang textbook. Plus 1. Plus 4 and 4. It's a plus 1. Anyways, negative 9 and 4 plus 4 and 4 will give me minus 5 on 4. So this here will be minus 5 on 4, and this will be equal to 0. Apologies for the bit of a mix up here. This is not negative 11, it's not negative 1, it's plus 1. Alright, now we can just go ahead, and because we have a difference here, this will be x minus 3 on 2 plus the square root of 5 on 4, and x minus 3 on 2 minus the square root of 5 on 4. And this is equal to 0. So please don't feel intimidated by the fact that there are surds and fractions involved. Just be mindful that it is there, and it can lead to silly errors. My silly error for the day is interpreting the question incorrectly, but that's a textbook's fault. So just be mindful when you're approaching questions like this, when there's fractions and surds involved. This here can be written as root 5 on 2, because you can separate this using the surd laws, and when you separate the square root of 5 and the square root of 4, the square root of 4 can be written as 2, or square root of 4 is 2. So we'll leave it in that format, and you'll see why, because this here, the denominators are showing to be the same, and we want that just to make the format look a little bit neater. 0. So this here can be written as x minus, and we can group these together because the denominators are the same, all over 2, and x minus 3 minus root 5 all over 2, and this is equal to 0. So this implies that x, I believe it's yep, x minus 3 plus root 5 on 2 is equal to 0, or x minus 3 minus root 5 over 2 is equal to 0. And then for both of them, we can just simply solve for x. For the first one, I'm just going to add a 3 plus root 5 on 2, and I'll add it to both sides. So this is implying that x is equal to 3 plus root 5 all over 2, or the second one, x is equal to 3 take away root 5 all over 2, because I'll just be adding the inverse of that, so plus 3 root 5 all over 2, and those are your two solutions right here. So the third example, despite the little hiccup at the start because the textbook had written the incorrect question at the start, it can be a bit intimidating, so just be careful with your surds. But other than that, go ahead and check your log sheet, see which questions you need to do for exercise 5H, and I'll see you in the next video. Bye bye.